This is Algebra 2 at Trig. This is section 7.2. We're graphing exponential decay functions. If you will recall, yesterday we graphed exponential growth functions, so now you'll see that the graph is a little bit different. For our exponential decay functions, we're going to be very similar to what we did yesterday. We have our b value. Often we talk about an a that sits out in front. It's got to be greater than 0, but the b value is different for these decay functions. It has to be between 0 and 1. The b value is considered the decay factor. So we look here at what a graph would look like. This equation is y equals half x. And the way I can tell that is that when you're at a certain point, the next point is half the amount of the previous, and then half the amount. So you're up at 4, and then 2, and then 1, and then a half, then a quarter, then a 16th, and a 32nd. This line here that the line approaches is the asymptote. The graph is never going to touch the asymptote. It only approaches it. And this arrow is actually that arrow. It's pointing to the line itself. So the equation is half x. Notice that when we read it from left to right, it falls. It's decaying. It's getting smaller every time the x gets bigger. Our points that we have are 0, a. When a is 1, it's going to be at 1. When a is 2, it's going to be multiplied twice that amount, so it's wherever the a is at. And 1, b. Our axis of symmetry is where the asymptote is for this parent function. So when y is 0, as long as there's no translation up or down, our asymptote is going to be at y equals 0. What type of numbers can we plug in? Well, when we look at the table, for y equals half x, for our x and the y, we can plug in negative numbers to get 1/4, or 1/2. You can plug in 0 to get the value of 1. Wrote those backwards, didn't I? You're going to take the fraction to flip it over. Let's try that again. Take the fraction and flip it over and square it. Take the fraction and flip it over, because it's a negative exponent, to the first power. Anything to the 0 power is 1. Anything to the first power is the base itself. And then from this point, it starts to get smaller. So notice how they get smaller every time. Notice that the domain, the x values, are negative, they're zeros, they're positives, they're all real numbers. The results you can get are called the range. The range are only the numbers that are greater than, not equal to, does not include 0, only greater than 0. Okay, like yesterday, let's try graphing 1/5 x. So we know this is exponential decay. Because the b value is less than 1, but it's greater than 0. We're going to make a table. So we're going to use numbers like -1, 0, and 1. The -1 flips the fraction over. The 0, anytime you have a base to the 0 power, it's a value of 1. And anytime you have a base to the first power, you actually get that base. So we can graph that out. we plot our points, and notice how these are different compared to the exponential growth. These are exponential decay. They're falling to the right. It'll approach the x-axis, but it'll never touch the x-axis. Then we always want to write the equation of the graph. The horizontal asymptote is y equals 0. Our domain is all real numbers, and our range is greater than 0. If we were to talk about end behavior, the end behavior, as x approaches negative infinity, as we look at x values that are smaller, the function is increasing. As x moves to the left, the graph, the range increases. So it goes to positive infinity. As x moves to positive infinity, as x gets bigger, the graph decreases. And it decreases not forever, actually not even to the 0. It approaches 0. It'll always get closer to 0, but it'll never reach it. Here we're going to do some transformations. We're going to take our b value, we're going to do a vertical stretch, and that's where the a really comes into play. The y-intercept of the graph will occur at 0a because we're multiplying by a value of the a to the 1, so we get the a value. The horizontal and vertical translations, those graphs are going to look like these equations, just like the exponential growth, except the b value is different. The b value could be between 0 and 1. We're going to stretch the graph, and then we will translate it horizontally h units and vertically k units. So our h and k, remember, it's always the opposite of what's inside here, and it's that amount. It's the opposite and the exact value of k. Opposite of the h, exact value of the k. So we'll try this one. We'll start out with a parent function. In this case, our parent function is 3/4 raised to the x power. And to do that, we're going to pick values of x that we can work with as we make the graph bigger and bigger. So x values of -1, -2, -1, 0, and 1. We know that 0 of any base always gives us 1. We know that 1 for any base, the exponent of 1 for any base, is exactly that base. The -1, what is that going to do to the base? That's going to flip it over. So now you're going to have 4/3. And the -2 is going to flip it over, but square each number. That's going to be 16/9, which 9 goes into 16 one time with 7/9 left over. So that's just a little bit under 2. So we come over here to our graph, and we're going to have our first point at 0, 1. Remember, we're just graphing the parent function at the moment. At -1, we're up at 1 1/3. At -2, we're up at 1 7/9. So that's like 1.777. So it's increasing very slowly. It's increasing to the left, but we call that decreasing to the right. And then we're at 3/4, and it follows that same type of pattern as we move. And that is y equals 3/4 to the x power. Now you notice that it has a negative, so there's a reflection over the x-axis. Parent function is reflected over the x-axis. So you're going to take all of those values and multiply them by a -1. So we'll graph this one out. And that's our graph of y equals -3/4 x. Notice that the negative is on the outside of the parentheses. It's not being affected by the x. Now we're going to, after we reflect it over the x-axis, this is going to be stretched. Vertically by a scale factor of 2. So you're going to go twice as much. So at the -2, that's almost going to be at 4. 1 1/3 is going to become 2 1/6. The -1 is going to become a 2. And the 3/4 is going to become 6/4, which is 1 1/2. And all the points are going up twice as much. But by the end, they're still approaching 0. So this graph is going to be y equals -2 3/4 x. And that's our final graph. There is no translation with this one. We don't have any h or k value. So our asymptote is still sitting here. We like to draw that in there and call that y equals 0. We have an asymptote at y equals 0. The domain is all real numbers. Now the range is a little tricky. It's the range of the purple graph. So its y is less than 0. And because of the reflection, now it's less than 0. We look at this graph, we see a parent function, and we see a translation. So our parent function is going to be 1/3 to the x power. So at 0, any base to the 0 power is 1. Any base to the first power is itself. -1 is going to flip it. -2 is going to flip it and square it. So at -2, we're going to go up 9. -1, we go up 3. 1, go to 1/3. Here we really see the exponential decay. So we're getting y equals 1/3 to the x power. So with our transformations, we are going to translate the parent function 2 units right, because it's a -2, 3 units left. So you can take every one of those points, and we're going to go 2 to the right, whoops, and 3, not left, 3 up, because it's a positive 3. So we go 1, 2 to the right, and 1, 2, 3 up. 2 to the right, 3 up, 2 to the right, 3 up, 2 to the right, up 3. So we see our graph is coming down, and it's approaching this same line. You got to be real careful that we're not trying to cross where the asymptote is going to be. Y equals the 1/3 x minus 2 plus the 3. We have an asymptote at the k value. So this is y equals k. In this case, k is 3. So there's your graph. Same type of graphs we've been doing in the past. We just got to start and figure out what does the parent function look like, and then you do the typical RST. The horizontal asymptote we saw was at y equals 3. The domain for all of these is all real numbers. You can plug in any positive or negative numbers. And the range are y values greater than 3 also. It'll always be where the asymptote is at. Okay, on our last page we have exponential decay model. That's when we have our value that is less than 1. We take our rate and we're subtracting it from 1. For whatever your time distance is. This is where we start, so it's our start point. This is our percentage. And that's the percentage decrease. So it's got a decrease because we're doing exponential decay. And this is, typically it's the number of years. It's the time frame when each calculation happens. Whenever that percentage, and typically it's years. Okay, a new flat screen TV costs $1,200. The value of the television decreases by 21% each year. Write an exponential decay model giving the TV's value after T years. So we have our starting point of 1,200. 1 minus. Now how do we write that percentage as a decimal? 0.21. So your best model is going to be 1,200.79 T. 1 minus 0.21 is going to be 0.79. What is the estimated value of the TV after 2 years? You want to buy somebody's TV 2 years old. It used to cost $1,200. Okay? I don't think you're going to get that for $1,100 or $900. Let's find out. So we're going to take our $1,200 TV. We're multiplying this by 0.79 for 2 years. And that gives us an approximated value of $748.92. So we can calculate out what is the television worth. If you pay more than that, then you didn't get a very good deal. If you paid less than that, then you got a pretty good deal. Using your graphing calculator, model and estimate the value of the television. When will it be $300? That's all the money I've got. So when is the TV going to be worth $300? So get your graphing calculator out. And we'll go to y equals. We'll type in 1200. 0.79. False alarm. To the second power, because we're trying to figure it out after 2 years, but no, we don't put a 2 there, sorry. We put an X in that spot because we're doing a graph. We want to see all the points. We don't want to see what it is after 2 years. We know exactly what it is after 2 years. So we can graph that. Now, where'd our graph go? Well, remember, we're starting way up here at $1,200. And when x is 1, and x is 2, and x is 3, all the way to x is 10. We're still up there at 113. So I need my window to look higher than a maximum value of over 1,200. So I'm going to pick a y value of 1,500. It didn't look like we needed to extend our x's out. We just needed to look higher up in the graph. So let's see what happens this time. There it is. It's exponential decaying. It's falling. It's getting worth less every year. So in our y equals, we're going to put down 300 to find out when does the graph exactly equal 300. Now we can calculate that location. What keystrokes do we need to make to verify where that intersection is at? Second trace. We go down to intersection. Hit enter. Now it asks us, is this our first equation? Answer is yes. Is that our second equation? Of course it is. Then it asks us for guess. Does these two graphs cross more than once? And no, the graphs don't cross more than once, but you're welcome to get closer if you want. Doesn't really matter. You get the same answer. So it looks like 5.88 years. Okay, at 5.88 years. Okay, so estimate when the television will be $300. At almost 6 years old, then it'll be worth $3. Okay, number 3. When an exponential function is raised to a negative exponent, this indicates a reflection over the y-axis. Because x is negative, it is going to flip the graph over the y-axis. When the a value is negative, it flips it over the x-axis. This is flipping it over the y-axis. It may be written with a positive exponent by changing the base to its reciprocal, which is 1 over b. So if we take this one, our equation, the 3 is not affected by the x, but let's not write it with a negative exponent. That flips the fraction over, and now going from 5 to 1/5, there's a reflection over the y-axis. The a value is 0, the b value is less than 1 but greater than 0, so this is called exponential decay, because the b value is less than 1. Let's try one more. Take a look at what you see here. So we have our f of x equals -2, a negative exponent, so we flip the fraction, so we have a positive exponent. But what you notice here is since the a value is less than 0, this equation is only considered exponential. Not decay, not growth. You typically want to call that growth. But because of the negative, the graph actually is falling. Good luck.